Here we go again. In our rate of change section for calculus, we're given the following. If a stone is thrown vertically upwards from the surface of the moon with a velocity of 10 meters per second, its height in meters after t seconds is h equals 10t minus 0.83t squared. In part A, we want to find what the velocity is after 3 seconds, and in part B, we want to find what the velocity of the stone after it has been risen 25 meters. However, before we get started on either one of these parts, let's look at a sketch graph of our height function. So here we want to look at our height function. We're going to factor out a t, and what we're left over is 10 minus 0.83t. We're going to set this equal to 0 so that we know our t-intercept is t equals 0. And our second one is going to be t is equal to 10 over 0.83. We're going to punch this into the calculator, beep, boop, 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 beep, and we're going to approximately give us back the value of 12 seconds. So now let's kind of sketch out our graph to see what we kind of have. We have our two intercept values. One of our intercept values would be at 0, 0. So let's plot that point. Boop. Then our second one is approximately when t is 12. And so that tells us our x-axis is going to be t, and we're going to set our y-axis to height h. We're going to have a downward facing parabola because in our original function, our t squared has a negative coefficient value. So we sketch our graph as a downward facing parabola going through our two intercept values as follows. And there we go. Now moving on. Part A. We want to find the velocity of the stone after 3 seconds. First, let's recall that the derivative of the position function would give us the velocity function. So what we're going to do is take the derivative of our position function, and this would give us 10 minus 0.83 times 2, t to the power of 2 minus 1. Then we want to simplify. So this would leave us with 10 minus 1.66t. And there you go. We have now our velocity function. Since we're looking at when the time is 3 seconds, we're going to let our t equal 3 seconds. So we're going to substitute this into our velocity function. So we have v of parentheses 10 minus 1.66 of parentheses. Then in each of these parentheses, we're going to substitute in 3. Now we continue simplifying. So I have 10 minus 1.66 times 3, and this would give us 4.98. Then we continue with our subtraction. So we have 10 minus 4.98, giving us 5.02. We just want to remind ourselves our dimensions is meters per second. So what's happening here is that at 3 seconds, we're seeing what's going on right here on our graph. And we're finding out that at this moment, when t is equal to 3 seconds, our velocity is going to be 5.2 meters per second. And that's it for part A. Time for part B. In part B, we're looking for what is the velocity of the sun after it has risen 25 meters. So we're going to take our original position function here and let h is equal to 25. So that we have 25 is equal to 10t minus 0.83t squared. Then we're going to set it equal to 0 and rewrite our equation as follows, as negative 8.3t squared plus 10t, and then we're going to subtract the 25 to the other side as follows. Now, what we're going to do here is we need to find the value of t. So in order to do this, we're going to use the quadratic formula. To remind ourselves what the quadratic formula is, there's a nice song, if you remember it, is t will be equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So if you remember this formula, that'd be great. Before we do any substitution into this formula, we want to make sure we define what our a value is. In this case, a is negative 0.83. We want to define our b value here, which is positive 10. And lastly, our c value is equal to negative 25. So we take this information and substitute it into our quadratic formula in order to get our possible time values. So we have as follows. After substituting into the quadratic formula and simplifying, we have two possible t values. We have t1 sub 1 is equal to 50 parentheses 10 minus the square root of 17 all over 83, and t sub 2 is equal to 50 times the parentheses of 10 plus the square root of 17 all over 83. Again, we just take our a value, b value, and c value from our quadratic equation. When we substitute h is 25, then we substitute it into the quadratic formula here, reminding us that, hey, we can remember this by minus b plus or minus the square root of b squared minus 4ac all over 2a. Then we simplify. And this is how we get our time value 1, t sub 1, and t sub 2. In order to get these secondary answers, we need to punch in the values into a calculator. So just go boop, 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 boop into our calculator, and then we have the following two t values. So what does each of these t values represent? Well, the first t value here, when it's approximately 3.5 here, this is the risen part. This is the going up direction. When we have the other t value of 8.5, approximately 8.5, what this represents is the fallen value. So we want to use the first value here because this is the risen value. Now we're going to substitute this value into our part A for velocity function. So from part A, we found the velocity is equal to 10 minus 1.66 times t. So what we're going to now do is substitute in 3.54. So we have v of 3.54 is equal to 10 minus 1.66 of 3.54. And again, in order to get our answer here, we're going to keep punching it into our calculator and go beep, boop, 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 boop. And this should give us 4.124 meters per second. And there you go. That's it for part B. And that's it for this question. Huzzah! We're done.